So this is the second part of this lecture, and what I decided to do is to skip a few sections. So the root and the ratio test will not be on a test. Will be skipped. I also will skip the power series. That is also skipped. And so finally I will say that I will skip most of the part of summation by parts. So this will be partially skipped. The only thing, what that means is that I'm going to skip theorem 3.41, and theorem 3.42, but I will need a theorem 3.43, simply because it will appear so much in our considerations later on. And Rudin proves theorem 3.43 using theorem 3.42. So since I skipped theorem 3.42, I am going to prove theorem 3.43 my own way. If you want to follow Rudin, you will need the theorem 3.41 and 3.42 to prove the theorem 3.43, or you can just prove this theorem directly. And what does this theorem deals with? Well, for now, we were mostly concerned with the convergence of the series of the form ak, k from, say, 0 to infinity, or k from 1 to infinity, where ak are greater or equal than 0. Okay. So what the theorem 3.43 deals with is the case when the terms of the series are not necessarily positive. And before I go on, let me just explain something to you. That, for instance, if the terms are not necessarily positive, many of the results that we studied before may not apply. So if the series, remember, if the series ak with absolute value of k converges, then we proved before that that means that this series converges, and we're done. Now, they don't converge to the same number, don't misunderstand me, but the convergence of this series implies the convergence of this series. The convergence of this series does not necessarily imply the convergence of this series, as we will see in a second. But before I start on a theorem and try to give you the exact result, let me give you an example. So remember that the series 1 over n diverges. So this is a series of the form 1 plus 1/2 plus 1/3 plus 1/4 plus etc. This series diverges. However, what I will conclude as a result of this particular part of the text is that if I look at the series 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, etc., then this series will turn out to converge. Okay. So what the general theorem goes as follows, and please be very careful about the details of this theorem, and the theorem looks like this. Suppose that b, n are positive numbers. I also going to assume that bn is decreasing, meaning bn plus 1 is less or equal than bn, so the numbers get smaller and smaller and smaller, and I'm going to assume that bn tend to 0. Well, that is kind of necessary, obviously. So now I'm going to look at the series of the following form. I'm going to look at the series minus 1 to the power, say, n plus 1, and from 1 to infinity. So this times Bn. So these are positive numbers, and what I'm going to do is I'm going to put the sign in front of them, so it will be B1 minus B2 plus B3 minus B4 plus etc. So this will be the series where all the b's are positive, but signs in between them will alternate. And these are called alternating series. And again, you probably know from Calculus 2 course that alternating series converges. That is, if all these conditions of the series are met, the terms Bn are positive, Bn plus 1 is less or equals than Bn, so Bn's are decreasing, they tend to 0, and if I form a series of this particular type, it's not the series of Bn, it's the series of Bn where the signs in front of Bn's alternate, then this particular series would converge. Okay, so this is the theorem, and I'm going to try to do a proof of this theorem. Okay, so I have the series sum of minus 1 to the power n plus 1 Bn, which is equals to B1 minus B2 plus okay, so the resolution came back, plus B3 minus B4 plus B5 minus B6 plus etc. And I'm going to assume that Bn plus 1 is less or equal than Bn, and I'm going to assume that Bn converges to 0, and now I claim that the resulting series converges. So in order to prove for me the convergence of this series, I have to look at the partial sums, and I'm going to look at two different kind of partial sums. One of them is S of 2n. So this is a partial sums with even index. And this will be equal to what? It will be equal to B1 minus B2 plus B3 minus B4 plus B5 minus B6 plus etc. B 2n minus 1 minus B2n. Okay. And when I'm looking at the series, I'm going to put the brackets around it, and the brackets are going to be put in this way. So notice that because B2n minus 1 is greater or equal than B2n, B2 is greater or equal than B4, B5 is greater or equal than B6. I'm going to conclude from here is that all the terms of the series are greater or equal than 0. Agree? And therefore S2n is greater or equal, or S2n plus 1 is greater or equal than S2n. Yeah, let me do it again. S2n. In other words, if I look at the sequence S2n, this is an increasing sequence. And in order for me to prove that this increasing sequence converges, I want to prove that it's bounded. So let me look at this sequence one more time. So S2n is equal to B1 minus B2 plus B3 minus B4 plus B5 minus B6 plus and so on, and this time I'm going, and the last term here will be B2n minus 1 minus B2n, and this time I'm going to put the brackets a little bit differently. I will say that this is equal to B1 minus B2 minus B3 minus B4 minus B5 minus B6 minus B7 minus etc. Now notice that b2 is greater or equals than b3, so this number is greater or equals than 0, and this number is greater or equals than 0, and this number is greater or equals than 0. So all these numbers are greater or equals than 0, and I subtract this positive number from the number b1, which is also positive, and so my conclusion is that this is less or equals than b1. So if I put it all together, I conclude that S2n is less or equals than b1. It is an increasing sequence, S2n increasing, and therefore I know that S2n converges. Let's say it converges to some index L. Okay, so now let me look at the sequence S2n plus 1. And this is the sequence of numbers which look the same way: b1 minus b2 plus b3 minus b4 plus etc. plus b2n minus b2n plus 1. And so if I look at the difference between S2n minus S2n plus 1, so if I'm going to subtract these numbers from these numbers over here, what I will have left is just one number, and this is the number b2n plus 1. So what is the conclusion from here? The conclusion from here is that b2n plus 1 tends to 0 as n tends to infinity. I know that S2n converges to L, and so therefore I also know that S2n plus 1, this sequence, because the difference between this sequence and this sequence converges to 0, I will conclude that S2n plus 1 converges, and in fact converges to the same number, and the number is L. So now, to put it all together, I will conclude that the sequence Sn, whether n is even or odd, it converges to the same number L, and so the series converges. Are you good on this? Okay. So, as a corollary from this, I'm going to deduce that the series 1 minus 1/2 plus 1/3 minus 1/4 plus etc. that this series converges. Okay, let's see. I don't know what it converges to, but once again I'm going to conclude that convergence is very, very, very fast, because the difference between Sn plus 1 and Sn is less or equal than that number bn plus 1, which converges to 0. So the convergence of the series is about as fast as the convergence of the series bn. Okay, so with that, I'm going to introduce this terminology that I tried to introduce before. I will say that the series sum of an converges absolutely if this series converges okay. And we proved before that if the series converges absolutely, then the series converges. Now the next term here is that the series sum of an converges conditionally. If the series an converges, but this series diverges. So for instance, the series 1 minus 1 over 2 square plus 1 over 3 square minus 1 over 4 square plus 1 over 5 square minus etc. This series converges absolutely, because the series with absolute values there will be 1 plus 1 over 2 square plus 1 over 3 square plus etc., which is the series sum of 1 over n square, and we know from before that this series converges absolutely. On the other hand, the series that I mentioned at the very beginning here, the series 1 minus 1 half plus 1 third minus 1 fourth plus 1 fifth minus 1 sixth plus etc., this series converges conditionally. Well, why do they converge conditionally? Because I know that the series converge. I just finished proving it, and I also know that this series with absolute values, so the sum of absolute values of n, will look like the sum of 1 over n, and this series diverges. Okay, so this is kind of a one theorem that I would like for you to take out of it, and now I want to talk about something else. So this will be a prelude to the last class in this particular chapter, and this is addition and multiplication of the series. So this is just an introduction to this topic. I will continue talking about it in the next lecture. But I have a series, say sum of an, and I have another series, say sum of bn. Okay, and in mathematics, whenever we have some objects, some new objects, we would like to add these objects, and we would like to subtract these objects, and we would like to multiply these objects. So like when we had sequences, we proved all the theorems about convergence of the sum of the sequence and convergence of the product of the sequence. Now we're dealing with series, and that means that I have to define, and I want you to pay attention to this word define. It kind of sounds like obsessive compulsive, but that's the way mathematics is. What I would like to do is I would like to define the sum of the series. So my first series here are equal to, let's say n starts with 1, n starts with 1 to infinity. My first series here are equal to a1 plus a2 plus a3 plus etc. up to infinity, right? And my second series look like b1 plus b2 plus b3 plus etc. And my point is that if I try to define the sum of the series, I cannot just say plus those guys, okay? Because now I don't have the series. I don't have terms which go to infinity together. So what I would like to do is I would like to define the new series Cn, and this new series will be called the sum of the series an plus the sum of the series bn. Okay, so notice that this thing as the series, this thing as the series, this is not the series. So I want to define something that looks like this, that looks like real series, which is the sum of those two series. So let's define it. So I'm going to do it in the most obvious fashion possible. I'm going to define Cn to be an plus bn, and now when I look at the sum of the series an plus the series bn, this will be the series of the form an plus bn, so each term with the same n added individually, and this is what's called the sum of the series. Again, I am sounding very, very obsessive compulsive, but if I go back to this particular series, of the form A1 plus A2 plus A3 plus A4 plus etc. plus B1 plus B2 plus B3 plus B4 plus etc. I could have also said that the series is equal to A1 plus A2 plus B1 plus A3 plus B2 plus etc. And even though formally speaking there won't be too much difference between the series, I still say that this over here is not the sum of the series. This is. So this is a definition. Given the series AN and the series BN, I define the sum of those two series AN plus BN as a series Cn, where Cn are equal to An plus Bn. Okay. So I spent here God knows how many minutes talking about this totally trivial and obvious stuff, but I'm doing it on purpose because I want to make sure that you understand that this is a definition. And while it seemed to be trivial, it is still a definition that you need to know. Okay. So what should be the theorem? The theorem will be, as you can guess, if the series AN converges and the series BN converges, then the series Cn, where Cn is equal to An plus Bn, converges. And in fact, not only the series converges, but they converge to what you would expect the series to converge, and that is if the series AN is equal to, I don't know, A, and the series BN is equal to B, then the series Cn is equal to A plus B. I hope it doesn't come as a surprise to you. It is completely to be expected. So let's do the proof of this theorem. Proof, I have the series AN, series BN, and series Cn equals to AN plus Bn. So now if I use Sn to denote the partial sum of the first series, AK, k from 1 to n, and say Tn to be the partial sums of the second series, k from 1 to n, of bk, and let's suppose that un will be the partial sums of this series, ck, k from 1 to n. Well, now what is it? This is a sum of ak plus bk, k from 1 to n. This is a finite sum, so now I'm back into high school arithmetic and I can do anything I want with it. This is equal to the sum of ak, k from 1 to n, and plus the sum of bk, k from 1 to n. This is perfectly legal because now I'm talking about the finite sums. And so that is equal to Sn plus Tn. And what I hope you do know is that from the part about the sequences that we studied, that if Sn converge to, what did I say, it converges to A, which means that this series converges to A, and if Tn converge to B, which means that this series converge to B, then Un, which is equal to Sn plus Tn, that converges to A plus B. Again, at this point, it's all trivial, but I want to emphasize that at this particular point, I'm using the theorem about convergence of the sum of the sequences. So un converges to a plus b, un are partial sums for this new series, and so the conclusion is that un converges to a plus b, and therefore the series ck converges and to the right thing, which is a plus b. Okay, so that puts me in peace with the sum of the series. What should we do next? Can you take a wild guess? Well, my next step is to try and define multiplication of the series. Okay, so now I have the sum of an and the sum of bn. In other words, I have things like this: a1 plus a2 plus a3 plus a4 plus etc., and there are infinitely many of those terms, and then I multiply it by b1 plus b2 plus b3 okay, plus etc. Maybe I should have started, I would have been better off, so let me rewrite it. I will start with a0, so it will be a0 plus a1 plus a2 plus etc. So I'm starting my indexing at 0, and I want to multiply it by b0 plus b1 plus b2 plus b3 plus etc. And so how do I multiply this series? Well, if I try to use some sort of a distributive law, I will multiply a0 by all of those, and I will have a series, and then I will multiply a1 by all of those, and I will have a series, and I will multiply a2 by all of those, and I will have a series, and now I will have to add this infinitely many infinite series, and I really don't know how to do it. I know how to add two series, but I don't know how to add infinitely many infinite series. So there is a canonical way of doing it, and I will try to explain it to you, and I will explain it to you using polynomials. So this is where polynomials come in very useful. Let me for a second look at this series in a following way. Let me say that this is a0 plus a1x plus a2x squared plus etc. plus an x to the power n plus etc. So if my x is equal to 1, then what I see here is exactly the same thing as what I see here. And I'm going to multiply it by b0 plus b1x plus b2x squared plus b3x cubed plus etc. And again, if x is equal to 1, then the series that I see in here are exactly the same as the series that I see in here. And now I'm going to multiply it like I would polynomials. So what would be the term in this product that does not contain x at all? Thinking about it? Well, it will be what will happen if I multiply a0 by a0 by b0. So now I have a0 times b0. Okay. All other terms in this multiplication will contain x. What will be the term that contain x to the power of 1? Well, this term will be what? a0 times b1 plus a1 times b0. Do you agree with me? What will be the term which contains x squared? Well, it will be what happens if I multiply this a0 by this b2. So it will be a0 b2 plus a1 b1. I multiply this x by this x, and then I will have to multiply this a2 by b0, and that's the only thing I can do with x squared. Now if you, and I will continue this way, let me do x cubed just for fun. I will have a0 b3 plus a1, and then I have to multiply it by b2 plus a2 multiplied by b1 plus a3 multiplied by b0. Do you agree with me? Okay, good. So what about those terms that you find very, very peculiar? Well, notice that the indices here with x to the power 0 and up to 0. With x to the power 1, the indices here 0 plus 1, 1 plus 0 add up to 1. And so I'm taking all possible terms of a's and b's where the indices add up to 1. Here the indices add up to 2. How do the indices add up to 2? It will be a0, b2, a1, b1. So 1 plus 1 is equal to 2, 0 plus 2 is equal to 2, and 2 plus 0 is equal to 2. Finally, in here, I will have 0, b3. So 0 plus 3 is 3, 1 plus 2 is 3, 2 plus 1 is 3, and 3 plus 0 is 3. And there is no other way of doing it. So let me just try to generalize it a little bit here. I'm going to try to keep this page visible just for a second. Let's see if I can do it. All right. Okay. So what I will see here is that if I have x to the power, say, k, what will be the indices in front of it? Well, the indices in front of it will be a0 bk, true? Plus a1 bk minus 1, plus a2 bk minus 2, plus etc., plus ak b0. In other words, these numbers over here, this is the numbers that I'm interested in, they form a finite sum, and here, whatever, m goes from 0 to k of a k of a m b k minus 7. So this is all possible ways in which I can get a's and b's in such a way that the indices will add up to exactly k. Okay, so now I'm ready to give a definition of the product of the series, and here's the definition of a product of the series. So if I have the series ak and I have the series bk, so this is a definition. I'm going to define the product of the series ak times bk to be equal to the series ck. Okay, well, what is ck? Well, ck is the sum of m from 0 to k of am bk minus m, and this is the definition of a product of the series. It takes a little bit time to adjust to, but this is a beautiful definition, and before I go on about this particular definition, I'll try to give you any particular example of this thing. Let me ask you, so before you listen to me further, pause after I ask you this question. Does this remind you of anything that you have seen before? And if you can think of anything, let me give you a hint. Okay, so let's see. Let me write it down in a little bit different way. C of k equals to sum of a of m times b of k minus m. Well, sum here goes from 0 to k. Have you ever seen anything like that before? Well, I claim you did. You probably have seen it in differential equations course, where, remember, this is the sum, and if I have infinitely many of those things, and if this are not m, k, and m, but x and y, then this sum becomes an integral. Remember how the integral was the limit of the sum? So this will look very much like an integral of ax by minus x, and this was nothing else, or integral of f of x g of y minus x. And probably when you study Laplace transform in differential equation, I am sure that you looked at this particular thing, and this was called the convolution of two functions f and g. So by analogy, this particular formula is often referred to as a convolution of the sequences AM and BM. Okay, AN and BN. Okay, so this is a new sequence, which is a convolution of these two sequences, and this is how product of the series are defined. Of course, you can guess what I would like to do next. Probably not this time, but next time on Thursday. What I will try to do is I'll try to prove something like this. I would like to prove that if this series converge and this series converge, then this series converge, and in fact it converges to the right thing, to the limit of this series times the limit of this series. Well, unfortunately, or fortunately, depending on the point of view, this result turned out not to be true, as we will see next time. However, if one of those two series converges absolutely, then this series indeed converges and converges to the right thing. So this will be the topic for next time, and what I would like to do at the end of the day today is to do a little cutesy problem. So let me take this favorite series of mine, which I told you before, and this is a series for E, and this is equal to the sum of 1 over n factorial, which is equal to the sum of 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus etc. So my numbers an are equals to ak, are equals to 1 over k factorial. Do you agree with me? And now what I would like to do is I would like to take the same series, the sum of 1 over n factorial, and this time I will think of it as the sum of bn, and my numbers bk will also be equal to ak, which is equal to 1 over k factorial. Okay, so what I want to do is I want to multiply this series, so I will want to multiply e by e as the product of the series 1 over n factorial divided by 1 over times 1 over n factorial. And what I want to do is I want to use the formula that I just introduced a second ago. Remember, here is the formula. And I want to see what is going to happen. Ready? Okay. So the series will be the series of the form Cm, right? Where what is Cm? Well, Cm will be the sum of a, k, b, m minus k, or let me do it Cn, which will be the sum of, let me rewrite it. So it will be the series Cn, where Cn is equal to the sum k from 0 to n of ak, an minus k, because remember, my second term, my b's here, are exactly the same as a's. So this is equal to the sum of 1 over k factorial times the sum of 1 over n minus k factorial. Do you agree with me? Where k goes from 0 to n. And if I write it down in a little bit different way, I will say, see the sum, k from 0 to n of 1 over k factorial times n minus k factorial. And please again pause the video and stare at this for a New York moment and say, that looks awfully familiar. And indeed it does. So what's missing here is this extra term. If I only had n factorial here instead of 1, then I would recognize this quantity as nothing else but the binomial coefficient. True? So, let's do this. Let's say that this is equal to this 1 over n factorial times the sum k from 0 to n of n factorial divided by k factorial times n minus k factorial. Alright. So now this is 1 over n factorial times the sum of n choose k and by binomial theorem, this is 1 over n factorial times 1 plus 1 to the power n. So this is equal to 2 to the power n divided by n factorial. And the conclusion here is that if I take my number e and I multiply it by e using multiplication of the series, the result will be the sum of these terms over here, so 2 to the n divided by n factorial, and this as a power series for e squared. Cool? Okay. Guess what the power series for e to the power 7 is? Well, it's equal to 7 to the power n divided by n factorial. And guess what the power series for e to the x is? Well, this is equal to the sum of x to the power n divided by n factorial. And as long as I define this e to the x this way, I really don't have to restrict myself to x being necessarily real. I can also assume that x is imaginary. So x could be an imaginary number, a plus bi. Are we good on it? Okay. So what Euler did using this particular formula is to define e to the power ix as being the sum of ix to the power n divided by n factorial, and I will leave it up to you to use this particular formula to prove that the series e to the I 2 pi is actually equal to 1, to 1. And this is the most beautiful and the most famous formula of all times. You've probably seen it like this: e to the 2 pi I equals to 1. So I take the most transcendental number ever known to mankind, e and pi. I take another number which is not even a number, it's an imaginary number, it's the I, and I put them all together in the right way, and I will get 1. And this is something absolutely remarkable. In fact, to the best of my knowledge, most of the people in the world rated it to be the most beautiful formula that ever existed. Okay, so what I will do in the last day, or in the last part of the chapter, is I will go about proof that the series converges, the multiplication of the series converges if one of the series converges and the other series converges absolutely. This is not true if, not necessarily true if both of the series converges but not absolutely. And finally, I will do one more beautiful result about the series, which is the last section of this chapter, and that's, I think it's called rearrangement. So this will be left for Thursday, but for now, study well, and I'll talk to you later in these very hard times of coronavirus. Thanks, bye.